So we talked in the last episode about the length of a vector, and now we're going to formalize that notion a little bit more. One thing that's important to understand about mathematics in general, by the way, is that math is whatever mathematicians decide it is. Okay, that's something that a lot of students are under a misimpression about, I think. Students sometimes think that math is what it is because it could be no other way, but actually mathematics is about defining things in a useful way. And so when we ask ourselves the question, what does it mean to talk about the length of a vector? What does it mean to talk about its size or its magnitude? Really, we can define that any way we want, and as long as we're consistent with our definitions, it'll all work out. And so the trick is to define it in a way that turns out to be useful. So if you take an example like this, let's say we have a vector x, that's our favorite letter apparently. Let's say we have it being this vector 4, 3, okay? So you might ask yourself, if we wanted to get a sense of how big that vector is, right? And a vector could be a bunch of different numbers, but we want to boil it all down to one number, which is something to do with its size. What are some ways we could do that? One thing we could do is we could say, okay, well, if I want to know how big a vector is, I'm just going to count the number of elements in it. And that's certainly a valid thing to do, and in this case, that's 2. So one way of measuring how big this vector is just to say the size is 2, right? Another thing we might do is we might add up the elements. And if we do that, then we get 7. And that would be sort of a measure of how big this vector is, right? Another thing we could do, which is what we did last lesson, is we could do sort of a Pythagorean theorem type thing. We could say, well, you know, this vector can be viewed as an arrow in two-dimensional space, where it's 1, 2, 3, 4 in the x direction and 1, 2, 3 in the y direction, so we could view it as that arrow there. And maybe when I ask myself, what's the length of this vector, maybe I mean that distance right there. And if you remember your Pythagorean theorem, the length of that side, which is the hypotenuse, is going to be the square root of the sum of the squares of the other side, so it's the square root of 4 squared plus 3 squared, and I happen to pick numbers where that turns out to come out easy. That turns out to be 5, right? So we could say the, Euclidean is what this is called, the Euclidean distance, and that's going to end up being 5 in this case. Another thing we could do is say, well, you know what? Maybe all that matters when I talk about the length of a vector is just what the biggest value is. That one might not have occurred to you, but it's certainly something we could do. We could take the maximum element, and that would be 4. Okay? So what we've got here is 4 different ideas of how to measure the length of a vector. And you might ask which one's right, and the answer is all of them are right. It all depends on what we want to measure, what we want to consider the magnitude of a vector. And our formal name for that is going to be the norm of a vector, kind of a weird term. But our notion of the size or the length or the magnitude or the bigness of a vector, we're going to call the norm. And actually all of those answers and many others can be right depending on how we want to define it. And what we're going to do is we're going to use this term called the LN norm, where n can be any number, and depending on what that number is, we're going to get one of those answers that we had on the previous screen. All right, so that seems a little bit weird, so let me kind of boil this down for you. The first one we're going to start with is the L2 norm, and if I ever don't mention which norm we're talking about, this one right here is the default. And the L2 norm is the Euclidean norm. And the way we're going to define that, like let's say our vector x is 4, 3, like we just had. The notation for this is to put a double bar, kind of like a double absolute value sign is kind of what it looks like, around x. And I'm going to say sometimes I'm going to put a 2 here as a subscript. If I omit the 2, though, it means the same thing as if I had the 2. So if there's no number here, the default is to be the 2, which is the L2 norm. And that is the square root of the sum of x1 squared plus x2 squared plus ... plus xn squared. Okay? So it's the sum of the squares of each of these different things. So in this case, it is the square root of 4 squared plus 3 squared, which, as we said, is equal to 5. Okay. This is the most common norm because this is sort of the as the crow flies distance, right? As we just saw, if we put this in 2 dimensions, we're basically saying what is the length of that thing as the crow flies. If I'm going to go from the point 0, 0 to the point 4, 3, what's the distance in space of that thing? Now, it may not be obvious to you that that would also work in 3 dimensions, but it does. If I have sort of a 3-dimensional thing here, right, it already gets weird. So I've got my x-axis going left and right, I've got my y-axis going up and down, and then I've got my z-axis, which is kind of coming out of the screen here in some ways, right? So if I said that I had the vector 4 in that direction, and then 2 in the y direction, and then 3 in the z direction, so you kind of got to imagine coming out towards us in the z direction some amount, right? So let's say that's the vector 4, 3, I forget what I said for the z direction. Let's say I said 4 again, right? So that means we're going to go 4 in the x direction, 3 in the y direction, and then 4 out towards us. We can find out the Euclidean length of that by taking the square root of 4 squared plus 3 squared plus 4 squared. So it's still the squares here, and it's the sum of the squares. There just might be more than 2, there might be 3, there might be 10. And that's where you can't even visualize a crow's fly distance type thing. But nevertheless, if I say what is the norm of, P, where P is defined as 1, 2, 3, 9, negative 6, that is going to be the square root of 1 squared plus 2 squared plus 3 squared plus 9 squared plus negative 6 squared, and you're going to get some kind of answer there, okay? So the default norm always means the distance as the crow flies, which is the Euclidean norm. Now, that's just an operation you can just carry out, right? It's just a matter of turning the crank and going through all those squares and all those, and then that square root, right? Okay, now, to give you some intuition here as to why it's called the L2 norm, it's the square root of, x1 squared plus x2 squared plus plus xn squared if it's got n elements. So I'm going to write the number 2 here, even though you don't have to put a 2. It means square root if you don't have a number there, right? But remember that another thing we could do is we could say, well, gosh, what's x1 cubed plus x2 cubed plus all the way to xn cubed, and take the cube root of it. That's a thing. And that is defined as the L3 norm. And if we said, hey, I wonder what x1 to the 4th power plus x2 to the 4th power plus plus xn to the 4th power is, all to the 4th root, that is what the L4 norm is. And if I said, gee, I wonder what x1 to the 193rd power plus x2 to the 193rd power plus plus xn to the 193rd power, all take the 193rd root of it. Now that may seem a completely bizarre thing to do, and it sort of is, but notice it's still the same pattern, right? I've got a 4 here and a 4 on all these. Here I had a 2 here and a 2 of all these. Here I've got a 193 and a 193 of all these. So one thing we could define is the L193 norm, and that would be equal to that formula right there. Now, one caveat that I want to mention here is that we always want to take the positive magnitude of those numbers here, right? So let's say I define my vector, let's define B, and we'll say that's 2, 0, negative 5, right? Now, when I talk about the norm of B and I don't mention any particular number, of course we know that by default what we mean by that is the L2 norm, and that is equal to the square root, I don't have to put a 2 there, but I'm going to just for clarity here, of 2 squared plus 0 squared plus negative 5 squared. Now, in this case, where it's an even number here, it doesn't actually matter that this 5 here was negative, because when you multiply negative 5 times negative 5, you get positive 25, right? As long as you're squaring things, it always turns out to be a positive number. However, that's not true for a cube, right? If I was figuring out, I wonder what the L3 norm is of that B vector, and I took 2 to the third power plus 0 to the third power plus negative 5 to the third power, now I'm potentially going to get in trouble, because negative 5 cubed is not going to be a positive number. That's in fact going to be negative 5 times negative 5 times negative 5, which I believe is negative 125, right? So what we're going to do for any case here, just to make it all easy, is we're always going to take the absolute values of these things before we square them, cube them, to the 193rd power them, or anything else, right? And again, you might look at this and say, well, that's kind of redundant. I mean, why bother taking the absolute value of something before you square it? Because squaring it's going to, take the negative number away. Anyway, true that, but just to make it consistent with all these different ones, whether it's the second power, the third power, the fifth power, the 193rd power, or anything else, let's just always make sure that we take the absolute values, and then we're safe, okay? All right, so let's go back to our original example here, which I've forgotten what it was, so actually we won't do that. We'll just use our current example here, which is 2, 0, negative 5. Okay, so one thing we might do is we might say, let's take the L2 norm, which is going to be the square root of the sum of the squares, but we'll absolute value them just to be safe. And we can figure out what that answer is, right? That's the L2 norm. Now, one of the other choices, you remember, in our first thing, one of the things that we thought of was, well, what if we just take the sum of the elements? And of course, again, in order to get a notion of the length, we want to take the absolute value of the sum, right? So we want to take 2 plus 0 plus positive 5. We're going to take the absolute value of all those things, okay? And that's going to give us 7 in this case, right? That is, believe it or not, the L1 norm. Because when you do this operation, when you just take the absolute value of each entry and then add them all up, that is really saying, let me take the absolute value of 2 to the 1th power, plus the absolute value of 0 to the 1th power, plus the absolute value of negative 5 to the 1th power, and let me take the 1th root of it. Now that seems really weird, and you may never have seen the 1th root, and you may never have seen something to the 1 power, but all that does is nothing, right? If you take a number to the 1th power, that's just the same as having the number. And taking the 1th root of something is basically just having the number again. You don't do anything else to it, right? It's not the square root or the cube root, it's the 1th root, which just leaves it alone. So the reason I write it like this is to make you realize that this formula we have right here, where we're just adding up the absolute values of everything, actually is the same thing as taking the 1th power of all the absolute values and then taking the 1th root of it, which fits in exactly with our formula, and that is why that is the 1 norm. So the 1 norm also has a special name. It's also called the Manhattan norm. It's also sometimes called the taxicab norm, and those are kind of bizarre words, but you'll see what I mean in a minute. So here's why it's called that. So let's say we go back to our two-dimensional case, and let's take a vector here, which was 4, 3, right? Okay, so if I ask myself, Euclidean distance, what is that? We've seen that that is the crow's flies distance, which is going to be 5, because if you plug that into the Pythagorean theorem, you realize that you take, the square root of the sum of the squares, and that ends up being 5. Okay, so if you think about it, that's how far it would take me, that's how far away this point here is from the origin as the crow flies. Now, the problem is that maybe I'm not a crow, okay? Maybe I'm in, and here's where the term Manhattan or taxicab distance comes up. Suppose I'm working in downtown Manhattan, okay, in downtown New York, and I want to go for lunch somewhere. And I say, hey, we're going to leave the office building for a while. We're going to go get lunch. Where do you want to get lunch? And somebody says, let's go to this Chinese place. Let's go to this Italian place. Let's get subs, whatever. So we decide on a certain place. And we ask ourselves, how long is it going to take to get there? Or more precisely, how far do we have to walk? Or how far do we have to take a taxi? You realize that we don't have a helicopter probably, right? The direction it is as the crow flies, and that distance as it is from our office building to the restaurant as the crow flies is irrelevant, because we can't go that way. What we have to do in downtown New York is we have to go a certain number of streets over, and we have to go a certain number of avenues up. And so all that matters is how many over we have to go and how far up we have to go. We're going to be forced to zigzag, right? Now you might say, well, what if we sort of zigzag it? Can't we kind of cut off some distance here? And the answer is no. If our restaurant is right there, then we could end up saying, well, let's go 2 blocks over, and then we'll go a block up, and then a block over, and then a block up, and then a block over, and then a block up, and then a block over. But if you realize adding up all those distances of going over and up and over and up and over and up, you'll realize that's actually the same distance as it would have been if we would have just said, let's go all over and then go up. Or if we had said, let's go all up and then go over. We're not saving anything by zigzagging, right? Because the total distance here on this red path is we had to go 2 over, and then another one over, and then another one over, and then another one over. And then we also had to go up and up and up. So either way, we had, I'm sorry, I did 5 there instead of 4, didn't I? Dadgummit. What I meant to do was make the point be there. But I think you see the overall gist of what I'm talking about here, right? It doesn't matter whether you choose to do all your overs and then all your ups, or whether you choose to do all your ups and then your overs, or whether you choose to zigzag it. The total distance you're going to be going is the same. And in this case, the distance we're going to be going is 7, right? Because I have to go 7 blocks east and 3 blocks north, and it doesn't matter what order I do that in. Okay, so sorry I messed that up with the 5 here instead of the 4. But bottom line is that the reason they call it the Manhattan norm or the taxi cab norm is because you can't go as the crow flies. You have to take the sum of the distances there. And of course it's the absolute value, right? If I had to go 4 blocks east and 3 blocks south, that would still be a distance of 7 blocks I have to go. So it doesn't matter that it's a -3 or a +3, right? So the sum of the absolute values is called the Manhattan distance. And that comes up a lot because it turns out there's a lot of different mathematical applications where really what we want is the sum of all the distances, absolute value distances, rather than as the crow flies, and that's called the Manhattan. And that is the L1 norm. Now, it's a little bit weird here, but we're going to kind of be a little bit free, and we're going to say the L0 norm ends up being the number of entries in the vector. Actually, we're going to define it as the number of non-zero entries. So that's a little bit arbitrary perhaps, but that's in fact how we're going to define it. If we say x here is the vector 3, 2, -5, 0, 6, we're going to say that its L0 norm, or we could write it like this, with a 0 subscript, is going to be 4. Because there are 4 non-zero entries. And it turns out that what we're going to care about is, if it's a 0 there, well then phooey on it, we're not going to really count it. But when we take the L0 norm, we're basically just adding those things up. And that's kind of, sort of, like saying 3 to the 0 power plus 2 to the 0 power plus -5 to the 0 power plus 0 to the 0 power. That right there is a big, big question mark for mathematicians, which is why we ignore it. Plus 6 to the 0 power, and take the 0th root of all this. Okay, I'm squinting a little bit and I'm putting all this in air quotes because this part here doesn't really work mathematically. But just kind of keep in mind that what we're trying to do here is be consistent with our definition, and we're trying to ratchet our n all the way down to 0. And really what that boils down to is simply counting the number of entries and ignoring the 0 ones. Okay? Now, the other extreme here is if we said x is, I keep forgetting what we did, but 3, 2, and 6, and -5, and 0, and 2, or whatever, right? If we said, let's take 3 to the, get this, infinity, plus 2 to the infinity, plus 6 to the infinity, plus -5, we're going to absolute value all these, -5, to the infinity, plus 0 to the infinity, plus 2 to the infinity, and let's take the infinity root of all that. Okay, now that might make your head hurt. It certainly does mine. But what this ends up doing, as you make this thing 2, and then 3, and then 4, and then 193, and you keep getting bigger and bigger and bigger in this number, and of course you're also making the square root, cube root, fourth root, 193rd root also bigger. In the limit, as you make that thing bigger and bigger and bigger and bigger, what ends up happening is you end up emphasizing only the largest element. It turns out that what really matters as you make that number bigger and bigger and bigger, and as you take the 50th norm and the 100th norm and the 1000th norm and the millionth norm, it ends up that all that matters is the biggest guy. And so you end up getting, as the infinity norm of this thing, you end up getting the maximum value, which is this. And of course, if the maximum value was negative, then we'd end up getting that instead, right? So let's say this was a 15 here, a negative 15. Then our infinity norm would be 15, not negative 15, because again, before we plug it into this thing, we're going to end up taking the absolute value of it, right? So we always get a positive number out when we take a norm. But what we're going to get out of this is going to be the biggest element. So to go back to our original thing, we had 4 ideas for how to measure a norm. How to measure the length or the magnitude or the norm of a vector. And basically, there's 4 different ways we're going to use. And you could do others, but we're going to do these 4. We're going to say that the 0 norm is simply the number of non-zero entries in it. We're going to say that the 1 norm, which is also called the taxi cab norm or the Manhattan norm, is simply the sum of the absolute value of the elements. The one we're going to use the most, and I'll even put a star by this, is the Euclidean norm, and that is the Pythagorean theorem thing. That is the square root of the sum of the squares. And if you sort of want to be consistent with the other one, we'll take the squares of the absolute values of the elements, right? And again, you just want to think of this as the crow flies distance. Shortest path between 2 points is a straight line, and so that's exactly what we're doing here. And if I don't mention any subscript on this thing here, I mean the Euclidean norm, because that's the most common one. And then the other thing we might occasionally do is do the infinity norm, and that is simply going to be the max element in terms of the absolute value. Max absolute value of an element. Okay? So the big picture here that I want you to see, if you've never really realized this about math, is that math definitions are whatever mathematicians decide is useful. And we could use any of these definitions or others. And so it turns out that there is no one right answer to what is the magnitude of a vector. Normally we're going to mean the crow's fly distance, but you can define it in these other ways as well. All right, so let's see if you understood this and do a little quick review here. Here is a vector. I've got a vector called P, and it has 3 entries, 7, negative 24, and 0. And I'm going to ask you here, what is the L0 norm of P? Pause the video and figure it out. Answer is, it's 2, because we're just going to say the number of non-zero entries in the vector. That is, by definition, the L0 norm of it. What about the L1 norm? What's the L1 norm of this vector? Answer is 31, because we're simply going to add up all the elements. And of course, we're going to add up the absolute value of the elements, because, you know, going south 24 blocks as opposed to going north 24 blocks, that's still 24 blocks, right? So we're going to have to take the absolute value of all the elements before we add them up. We're going to end up getting 31. What about the Euclidean norm, which is the L2 norm, and which is also just the norm unless I say otherwise? What's that going to be? That's going to end up being 25. Again, I picked numbers that worked out nice, because if you take the square root of 7 squared plus negative 24 squared plus 0 squared, you end up getting the square root of this thing, which gives you 25 as the answer. And lastly, what about the infinity norm? What if I want to take the L infinity norm of P? Now I'm going to get the max absolute value of any element. So the notation here says if I make I be any number, I can look at P of 1, P of 2, P of 3, all the different elements of it. What is the maximum magnitude of any of the elements? And the answer here is 24, because that's the biggest one, right? Now, one more thing about norms before we move on to the next segment. We're going to talk occasionally about normalizing a vector. Okay, so you have a vector, and we're going to say we want to normalize that thing. Now, what does that mean? Well, all it means is dividing by the norm. Normalizing a vector just means dividing by the, and I'll put the in quotes here, norm. The reason I put the in quotes is because, of course, I have to tell you what norm we're talking about here, right? So the norm, well, what norm are we talking about? If I don't mention a particular norm, of course, I mean the Euclidean norm, right? By default, this is going to be normalized according to the Euclidean norm, which is the crow's fly distance, which is the familiar Pythagorean theorem thing. So let's do an example. Let's say I have the vector 4, 3. How do I normalize that? Well, normalizing would give me the vector 4 over 5 and 3 over 5. How did I get that? Well, because we know that the Euclidean norm of this vector is 5, right? Because that is the square root of 4 squared plus 3 squared. I chose numbers to make the math come out easy. So all I do is divide that vector by 5, which, if you remember what scalar multiplication does, when you scalar multiply a vector, it just means dividing each element by that thing, just like scalar multiplication is multiplying each element by that thing. And so all I do is divide by 5 here. Now, you might ask, what does it mean? Why do I call this the normalized vector? Well, if I ask myself, hey, what is the norm of this? What's the norm of the normalized vector? That is going to be the square root of 4/5 squared plus 3/5 squared. And if you work all that out mathematically, you will discover that turns out to be 1. So normalizing a vector simply makes it have norm 1, okay? Now you might say, well, why would I do that? Didn't I just wipe out all the interesting stuff? No, because here's why. Remember, a vector has two things. It has direction and magnitude. So in 2 dimensions, it has an angle with respect to the x-axis, and then it has a length that it is. And those two quantities define what a vector is. So when we normalize a vector, what we've done is we've said, let's preserve the angle, but let's just make the norm 1. Let's make it length 1. And by doing so, we end up having a norm 1 vector. We know it's going to be radius 1, and we just want to know what the angle is. Now, you might ask why I do that. Here's why. Because this allows, or prevents, I should say, Jezebel from cheating. Okay? So if you go back to our matchmaker.com example, right? Let's say I have, Jezebel, and she's gone onto the site, and she's filled out the survey answers, right? And we also have a bunch of eligible young men on this site. Let's say Biff, answered 3 to the first one, and 4 to the second one, and 0, and then 10, and then 0. Those were his 5 survey answers. And then we have Joe. He's also an eligible bachelor. And he really said, I love hand gliding, and I really love, romantic dinners, but I really don't like, I really don't like reading, and I really don't like playing video games, and I really don't like movies or whatever, right? And we have, Chad, and maybe Chad's kind of in the middle on all these, kind of 5, 5, 5, 5, 5, or whatever, right? Okay, and we said, what if Jezebel wants to get the attention of all these young men? She wants to maximize her chances for a great date, What she could do is she could just say, well, heck, I'm just going to answer 10 to all the survey results, right? And that way, my dot product with Biff is at a maximum, and my dot product with Joe is at a maximum, my dot product with Chad is at a maximum. So heck, that's my way of trivially maximizing what all of the different norms are, simply by making all my results at the maximum. What we're going to do is we're going to say, here's the deal, Jezebel. And for that matter, here's the deal, Biff and Joe and Chad and everybody else on the site. You're going to answer the survey questions however you want to answer them, and that's fine. You're going to get your vector, but then we're going to normalize you. we're going to normalize your vector. And what that does is it levels the playing field. It basically says, you know what, if you want to answer maximum value for every single survey answer, be my guest, but you only sort of get to spend that once, because we're going to take your vector, no matter how big it is in different directions, and we're going to shrink it down to be norm 1, which means you sort of only have a certain amount that you can spend on all of your survey questions. And by doing what Jezebel did, she's basically put her in the same boat as Chad, right? She's put herself in the boat of saying all equal on all the survey questions. And so that doesn't really help her max out all of the different guys that she could possibly pair it up with, right? Instead, what that does is that says, well, I'm going to end up being the same as Chad, because Chad also answered 5 to all these things, right? So essentially what we're going to do is say, okay, you got all these 10s, great, but you know what? We're going to divide by your norm. And we're going to divide by your norm, which is going to be the sum of 10 squared plus 10 squared plus 10 squared plus 10 squared plus 10 squared. Take the square root of that. And therefore, each of these vectors is going to be pointing in a different direction in 5-dimensional space. Biff's is pointing in the I totally love rock climbing, but totally hate these other two and are kind of middling on these two direction. Joe is pointing in the, boy, I totally love hand gliding and I also totally love creative writing and I hate the other ones direction. Chad is pointing in the equal in all aspects direction. And Jezebel is also pointing in the equal in all aspects direction. And so in this case, Jezebel is going to be paired up very well with Chad, but not very well with the other ones, because she is all survey questions even instead of being maxed out on the 4th one as Biff was, or maxed out on the front 2 as Joe was. Okay, that whole thing is easier to think of if you think of the 1 norm, right, where you sort of say that we're going to divide by the sum of your entries. Then that sort of says, well, Jezebel's got 50 points to spend or whatever, right, and she can put, or not 50 points. We're going to say she has 25 points to spend. And she could put 5 in each one. She could put 10 in the first 2 and 5 somewhere else. But her total ends up having to add up to that. And if she puts more than that amount, we're going to divide by her total to drop her down to where the average is going to be 5. If she puts less than that on average, we're going to bump her up so the average is 5. And that basically puts everything on a level playing field. Right? So that's what normalizing a vector does. It just means divide by the norm. And that gives you the same angle, but it gives you a norm of 1, a magnitude of 1. All right. So back to our quick review here. What if I said, here's my vector, I want you to normalize it. And I'll say you normalize it according to the Euclidean norm. Now what are you going to get? And the answer is you're simply going to divide each element by 25 because the Euclidean norm of it was 25. And then if I say, hey, what's the norm of the normalized version of that? You remember we divided by 25 and we got that version there in green. What is the Euclidean norm of the normalized version? The answer, of course, is going to be 1, because by definition, the norm of a normalized vector is 1. That's what it means to normalize it, is to restrict its magnitude or expand its magnitude if it started out with a magnitude of less than 1 in order to make it exactly 1.